So today we'll be looking at parallel RLC circuits. So these circuits consist of resistance, inductors, and capacitors. So before we dive deeper, we will have to look at frequencies. So these frequencies will be using them in our parallel RLC circuits. So we have the NEPA frequency, which is equal to 1 divided by 2 RC. And then we have the resonant radiant frequency, which is equal to 1 divided by the square root of LC. Now, before we dive deeper, let's familiarize ourselves with RLC circuit responses. So what I do is that I usually put the resonant radiant frequency on the left hand side and the NEPA frequency on the right hand side. So just to remember very well during the test. So I just put this on the left and then I write my signs in the middle. So when we have the resonant radiant frequency less than the NEPA frequency, we have an overdamped response of an RLC circuit. And then when the resonant radiant frequency is greater than the NEPA frequency, we have the underdamped response. And then when the two are equal, we have critically damped circuit response. So now let's look at the overdamped response of an parallel RLC circuit. So in many cases we will be using this equation right here. So the full characteristic equation for an overdamped response parallel RLC circuit. So as you can see, we have S1 and S2 right there. So those two are the roots of the equation. And then we have A1 and A2, and those two are constants. So we have these two as constants. And then to find the constants, we're going to use these two equations. So I can call this equation 1, and then we can call this equation 2. So how do we find the roots of an overdamped response parallel RLC circuit? So the roots have their own equations of finding them. So let's start with the first root, which is S1. So S1 is equal to negative the NEPA frequency minus the square root of NEPA frequency squared minus the resonant radiant frequency squared. So this is the equation to find the first root of the full characteristic equation. So the second root is similar to the first root, but we have to change this sign into a positive. So we're going to have negative NEPA frequency plus the square root of the NEPA frequency squared minus the resonant radiant frequency squared. So now let's get back to finding the constants A1 and A2. So we're going to be using these two equations simultaneously. So we're going to solve these two equations simultaneously. So what is VO? So VO is the initial capacitor voltage. So we have the initial capacitor voltage right here. So A1 plus A2 will be equal to the initial capacitor voltage. And also we're going to have the initial capacitor voltage right there. And then we are going to have IO, which is the initial inductor current. Now, one may ask, what does overdamped circuit response mean? Well, this is when the circuit settles back to normal, like going back to zero current or voltage, without bouncing or wiggling. So you can think of it like this. So you can imagine a heavy door with a super strong closer. So it shuts down slowly but doesn't swing back and forth. So the key idea is that too much damping or resistance kills the bounce, making the response very stable. So let's do an example. So we have a parallel RLC circuit on the left with a capacitor, inductor, and a resistor. And then we have an instruction for VO is equal to 12 volts and IO is equal to 25 milliamps. Find the characteristic equation for VT. So the first thing that we have to do, so step one always is to find VO and V and IO, which we are already given. So we're going to skip this step, and then we are going to move on to finding the frequencies. So let's start with the NEPA frequency. So the NEPA frequency is equal to 1 divided by 2 RC. So we already have resistance and capacitance, so we'll just take them from the graph, the picture. So let's get that. So we have 1 divided that by 2, and then we have the resistance, which is 190 ohms, and then we have the capacitance, which is 0.2 multiplied by 10 to the power of negative 6, and then you will get the NEPA frequency of 13,157.9 radians per second. Now we're moving on to finding the resonant radian frequency, so which is equal to 1 divided by the square root of RLC. So you can also rewrite this like this, so you can say this is equal to, so just square both sides and then you remove the square root. So now this is going to be equal to 1 divided by the inductance, which is equal to 50 milliamps. So we're going to put that in, so 50 multiplied by 10 to the power of negative 3, and then the capacitance, which is 0.2 multiplied that by 10 to the power of negative 6. Then plug that into your calculator and you should get 10 to the 8. So we're going to have 10 to the 8 radian squared. Remember, we squared, so it's going to be a radian squared per meter squared. So now that we have the frequencies, we have to determine whether the circuit is truly an overdamped response. So how are we going to do that? So remember, for a circuit to be an overdamped response, so we're going to have the resonant radian frequency squared being less than the NEPA frequency squared. So this condition right here has to be met. So let's check that. So we have the NEPA frequencies there, so we're going to square that and check. So after squaring the NEPA frequency, we can already see that the NEPA frequency is indeed greater than the resonant radian frequency. So this condition right here is met, which means our circuit is an overdamped response. Now, what is the next step when we have an overdamped response? So we have to find the roots of the characteristic equation. So we have to find S1 and S2. So let's go ahead and find the first root. So the first root is equal to negative NEPA frequency, that should be positive, plus the square root of the squared of the NEPA frequency minus the square of the resonant radian frequency. So let's plug everything into this equation and get the root. And we get the root of negative 4,606 radians per second. Now let's find the second root. So the second root is equal to negative NEPA frequency minus the square root of NEPA frequency squared minus resonant radian frequency squared. So let's substitute and get the second root. And we get negative 21,709.5 radians per second. Now that we have the roots of the equation, we have to move on to the next step. What is the next step? To find the constants of the characteristic equation. So to find the constant, we're going to use two equations simultaneously. So the first equation is A1 plus A2 is equal to the initial capacitor voltage. And then the second equation is going to be A1 multiply that by S1 plus A2 multiply that by S2 is equal to 1 divided by the capacitance multiply that by negative the initial capacitor voltage divided by excuse me divided by 3. Why did I say 3? Divided by the resistance. So I got a little flu, so sorry about that. So and then minus the initial inductor current. So we already have these two. We have this one and the inductor current. So we're going to substitute everything that we have into these two equations. So we can call this equation 1 and then we can call this equation 2. So let's start with the first equation. So A1 plus A2 is equal to the initial capacitor voltage, which is 12. And then we are going to move on to the second equation and substitute everything that we have. So we don't have A1, so we have S1, which we found previously, which is minus 4,606. So we're going to substitute that minus 4,606 and then plus A2. We also don't have that, so we're going to substitute S2. So S2 is negative 21,709.5. So we're going to have negative 21,709.5. And all of that is equal to 1 over capacitance, which we had previously. So the capacitance is 0.2 multiplied by 10 to the power of negative 6. So we're going to put that there, 0.2 multiplied by 10 to the power of negative 6. Multiply that by negative of the initial capacitor voltage, which is 12. So we're going to have minus 12 divided by the resistance. So the resistance was 190 minus the initial inductor current. So that is let's check that quickly. So we're going to have, what is it? Oh, right there, 25 milliamperes. So we're going to minus 25 multiplied by 10 to the power of negative 3. So we can put this into the calculator just to simplify the second equation. So after simplifying the second equation, this is what we have. So we have equation 1 and then equation 2. So just to save time, you can plug this into your calculator just to save time. And we found that A1 is equal to minus 10.5 and A2 is equal to 22.5. So now we come to the final step to write the characteristic equation for Vt. So Vt is equal to A1 multiply that by e to the power of S1t plus A2 e to the S2t. So this will be equal to the constant A1, which is minus 10.5 e2 the first root. So the first root is minus 4,606. So we're going to have minus 4,606 t, don't forget the t, plus a2, which is 22.5 e s2 the second root, which is equal to minus 21,709.5. So you're going to have minus 21,709.5, multiply that by t. So this is the characteristic equation for V. So let's say for T, let's say V here, and T is greater or equal to 0.